Good afternoon, everyone. My name is Harry Schnabel, and I'm going to be presenting on deflection-based design as it was applied to the Capitol Crossing excavation support system in Washington, D.C. So some of the outcomes that I hope you guys get from this webinar are, one, you can understand the causes of building settlement and damage that can occur from an adjacent excavation. Two, recognize how much settlement and deflection a structure can experience before showing signs of damage. And three, identify what we can do to limit the damage to a structure due to an adjacent excavation. First, I would like to go over briefly traditional design, which I'm sure a lot of you are familiar with. Traditionally, when we do a strength design, we apply a pressure to the back of the wall. This consists of the earth pressure. You might have water pressure if you're below the water table in a cutoff wall. You might have some building surcharges. You might have some other structural surcharges. Above grade and then below grade, you have active and passive resistance on the front and back of the pile. And then you typically, to size your member, you would calculate your maximum moment either at the cantilever or between the tiebacks and divide it by your allowable stress to get your required section modulus. Then to get your tieback loads, you would either sum up by area or some moments, or use some program to calculate your tieback loads based on the earth pressures that you've assumed. But what about deflection? This really doesn't tell you how much your shoring is going to move. It just tells you it's not going to fail structurally. So there are a lot of different methods of calculating deflection. One of them is to use the finite element method. A program similar to Plaxis might be used. There are some empirical methods. This is what we're going to be going over today as an empirical method. And there's also some other methods. I know some of the shoring programs that are available have modules that can estimate the deflection of your shoring system based on the earth pressures. So what are some of the sources of deflection in construction of an adjacent excavation? One is just the lateral movement or bulging of the excavation support system from the pressures that are from behind it. You might have bottom heave if you're in a deeper, softer clay. You might have settlement of the soldier beams if you haven't driven your soldier beams to a suitable strata, and you might have some pull down from the piles, and as the piles pull down, they'll probably be pulled out a little bit. Another big one is dewatering and lowering of the groundwater table, and I see this as two problems. One is if you lower the groundwater table in the surrounding soil, you increase the effective stress, and that causes settlement. And then also, if your wells are improperly designed, they can pull in fines from beneath the structure, and that can affect the settlement. Then there might be loss of ground due to construction. If you have a careless contractor out there, you might have tiebacks or soldier pile holes caving underneath the building, which could cause settlement. You could have washing out of the soil behind the lagging or raveling because the lagging wasn't properly backpacked. You might have loss of soil through tieback penetrations below the water table due to the differential head. You know, water wants to come through when you pierce a cutoff wall, and that might bring some fines with it. And then if you have an underpinning structure, of course, you have to remove part of the support, and that could lead to some settlement. Then, of course, construction vibrations from either driving or vibrating piles, or pretty much any method you use is going to have some vibrations, some just a lot more than others. Then there are a bunch of other sources like compressed air from drilling, maybe grout pressure, temperature fluctuations on braces can cause settlement. You might have a landslide that you didn't know about, or maybe you did know about it, or an earthquake. Might have a sinkhole, other issues. So when should you be concerned about whether your structure is susceptible to damage from, I'm going to focus on the lateral movement and bulging from the pressures behind the wall. and it can happen up to 3/8 away in all soil types, usually in better soils. You don't have to be concerned if you're more than 2H, and H is the height of the cut. And then within H, you really should be concerned about it. And then you also have to know what your adjacent building is. Is it on deep foundations, or is it on have a deep garage that's bearing below your new structure? Then you really, that mitigates some of the problems. And also, this is just for bulging and for lateral movement. You know, the effects of dewatering can extend further, and there might be other things that could extend even further. So when the shoring moves, adjacent structures moves both laterally and settles vertically. This causes, differential settlement because the thing settles, and also some lateral strain because the building moves. The back of the building is stationary and the front of the building is moving towards the excavation. So this kind of shows, these charts were developed by, I don't know who, but they show the angular distortion and lateral strain. And if you go on this chart that was developed in this paper, you can see, you want to be down in the negligible and very slight damage down in the lower left corner. This is where you want your excavation to be. So I'm going to go through some of the classifications of damage. Negligible damage is basically you have some hairline cracks, something that can easily be fixed with a coat of paint. Very slight damage, maybe a little bit wider, maybe a few little hairline cracks in the exterior brickwork. And I should point out that this is for masonry structures. The amount of damage is also highly dependent on the type of structure that you have. So masonry are what we're focused on here. Might have some slight damage where you start to get some windows sticking and due to the differential settlement, and then some lightly bigger cracks, then a little bit bigger, doors and windows start sticking, utility services might be interrupted, might have some weather tightness issues, the cracks are a little bit bigger, which is moderate. And I have some pictures here. This was from a structure that we did, and this wasn't actually from our shoring, but I showed some moderate cracks. This occurred because I think there was a unknown utility under the structure that when they dug down, they opened it up and it collapsed. And then you get to the real severe damage where you have to start thinking about whether or not you need to tear down your structure. This is what you don't want. So now I'm going to go over our case study, which is the Capitol Crossing in Washington, D.C. I'm going to do an overview of the project, but I was pointed out to me today that there's also a feature article on this project, which goes over the general history of the project in the latest issue of Geostrata. So if you want some more information about this structure, I suggest you read that article. So basically, this was a building that was built in the air rights over I-395, which is a highway that goes through Washington, D.C. We had excavation support on the two sides, and then we also had some micropiles. Another contractor put a slurry wall in. There were caissons to support the new structure. It's bounded by E Street, 3rd Street, 2nd Street, and Massachusetts Avenue, and I grew up in Washington, D.C., so I kind of know where this is, and it's right downtown near the Capitol. But it was an interesting project because most of the structures are actually supported above I-395, and I-395 basically became a tunnel. So the area that we're interested in is in this blue down here at the bottom. And that's where there were a bunch of structures that were adjacent to the deepest part of the excavation. This is what the project looked like beforehand. This is I-395. As you can see, it's just a regular highway right through the middle of D.C. So the Capitol Crossing project had over 130,000 square feet of supportive excavation. 1,300 tiebacks. The maximum height of cut was 72 feet. It consisted of just drilled and driven piles. We also had some braces where we had some ramps that went in. We used cross braces. We also had some structures that were underpinned using conventional hand-dug concrete piers. We had some walls that were used, single auger soil mix walls, where we designed the shoring for a surcharge from the buildings. There was also, like I said, a slurry wall that went through the middle of the site that was installed by another contractor, but we installed the tiebacks. And then, not to be left out, we decided to add some micropiles. There was some micropiles in the project as well. Soil conditions were typical of Washington. Typically, we had some fill, 5 to 10 feet, the maximum thickness of 27 feet over an alluvium of sand and gravel and cobbles with the occasional layers of clay over the Potomac group. So these are the structures in that area in blue that we were concerned about. There was an office building called Building 633, the Casa Italiana, and the Holy Rosary Church, which also had a bell tower, which was inconveniently located at an outside corner or excavation support system, which is the most difficult area to support. The bell tower was over 85 feet high, so we really had to be concerned with that. That's something that even a little bit of settlement would show up. And all of these structures were on shallow foundations, footings, and small mat. So how do we support everything? We used a combination of bracket piles on some of the structures, hand-dug concrete piers. Hand-dug concrete piers were used at the bell tower, and then there was a shallow excavation at the Holy Rosary Church. And then we used the drilled-in soil mix piles along the office building 633 and the Holy Rosary Church. And then we used conventional beams and lagging where we were away from the structures. And the Holy Rosary Church is kind of what we're going to be looking at as far as looking at the deflection-based design. So this is a cross-section through the Holy Rosary Church. We have multiple tiers of tiebacks supported by a single auger soil mix wall. And then we estimated the building surcharge using books and ESC and applied that to the back of the earth pressure diagram. We were below the water table, but because this is a soldier pile and lagging system and free draining, we didn't put any water pressure on the project. So what are some of the assumptions we made when we did the deflection-based design? One is that the volume of the ground surface settlement is equal to the volume of lateral movement. So however much the shoring moved out, that was the volume of the settlement. Two was that the settlement follows a parabolic profile with the maximum settlement at the shoring face, and it reduces to 0, in this case at 2H, but depending on the soil type, it might be as much as 3H. And then the maximum settlement is equal to 1.5 times the average lateral movement. And this is true for stands. It's different for other types of soils. Then we also had to look at the different stages of construction and how that affected movement, because everything is, we have to combine everything. So, you had your cantilever moment when you first installed your first tier of support. So you get a little bit of movement there. Then you get lateral bulging as you install the tiebacks below each tieback, and then rotation and leaning up the tieback wall as it settles. So the technique that we used on this project was, first we calculated what's known as the flexibility ratio, and I'm gonna cite all the papers where we got all these techniques. So I'm not going to go through a detailed analysis of how we did this. I think the best thing is to read all the papers and sort of figure it out. So the flexibility ratio was defined as the Young-Secant modulus of the soil times the distance between supports cubed divided by the modulus of the wall, which in this case would be steel, 29,000 KSI, and the moment of inertia of the SOE wall. And typically when we design these things, we don't account for the soil mix. We just take the moment of inertia of the soldier beam that we have in the soil mix. And using that, you can use a relationship to calculate the or estimate the lateral volume. So this is the relationship that we use to calculate or estimate the normalized volume from the flexibility ratio. Oops. You can see this down here is the volume. So using this, you calculate your volume, and from the volume, you can calculate the settlement, using the assumptions that we made that the volume of the lateral movement is equal to the volume of the settlement and follows a parabolic profile. And you can also calculate the maximum settlement at the pile by multiplying the average lateral movement by 1.5. The other thing that was important on this project, because it was so critical, was to make sure that we had sufficient monitoring. So we had, the typical auto station with a lot of prisms all over particularly at the bell tower and all over the structure. We also installed some inclinometers in our piles, and we installed some tilt sensors to measure interior column movement. And these are the results. We got fairly decent agreement between what we estimated and what was measured. Some of them were off a little bit, but for the most part, they were within at least, reasonable. There are a lot of things, obviously, that the actual movement would include all of the different sources of movement, so it's hard to separate out what was just for lateral movement and bulging. So in conclusion, I would like to say that, it's you can never guarantee that a building within the zone of influence and excavation will see zero damage, although sometimes people want that. It's impossible. You might limit the settlement to where you even don't say any negligible damage and no hairline cracks. At the capital costing project, we were able to meet the design goal of limiting building damage to very slight or negligible, which means they might have had a few hairline cracks, but there was no structural damage to any of the structures that we supported. And then that the deflection-based design method developed by Grouting et al. Estimated lateral and vertical building movements that were reasonably close to the actual building movements. And then I guess the third is for any excavation adjacent to an existing building, the SOE design intent is to limit potential damage to the building. Selecting the earth pressure and surcharge pressure diagrams is just one step in designing the SOE. It is essential to consider the stiffness of the SOE in the design as well. And acceptable potential damage should be agreed upon in advance. So when you're doing a excavation support system next to a structure, you have to let the owner know that there is a possibility of damage. And, by increasing the stiffness, which obviously increases the cost, you can limit that damage and try and get it below reasonable levels. And these are some of the papers that I talked about that we use to help us design our method for excavating deflection. I think these are some good papers if you guys want to get a hold of them and learn some more about this. And that is it.
Well, thanks, Hank. If anyone has questions, please type them into the Q&A. We have a couple. The first one I was going to ask you is, did you guys have a contingency plan if during construction things started to move more than expected? And if so, could you give us a brief overview of what you might have done to limit that?
Glenn, I'm going to be honest with you. I actually wasn't going to present on this, and I'm sure we did have a contingency plan, but Harold wasn't able to present this day. But typically, as a contingency plan, you would have, you would put in additional tiers of tiebacks, or as a last resort, you would backfill the wall and then rethink it. But a lot of times I think in one area we did actually put in some extra tiebacks, and I'm not sure if that was because the wall was moving or because there were some failures, but that's usually what we do. If you saw some of those tiebacks were on whales, which might mean that they were added later.
Okay. Another question that came up is how did you install the anchors? Did you use a high pressure system for grouting them? And do you know if there was any effect, any noticeable issues as you were putting the anchors in?
I think these were regrouted anchors. So typically we would put them in and then without pressure and then come back and regrout them. And there might have been, I'm not familiar with it. You could probably email Harold, but there might have been some issues with the slab, but I'm not 100% sure.
Okay. Are there any other questions from anyone in the audience? If you'd like to pose a question, type it in the Q&A box. Okay, here's one, Hank. Did the client provide performance criteria? Do you prefer a performance criteria to negligible?
Yeah, I think we would probably prefer a performance criteria. And I've seen it spec'd a couple of ways. I haven't seen it a lot, but sometimes the engineer will specify a stiffness for the system. So you have to come up with a stiffness based on your distance between supports and your the stiffness of your soldier beams or your vertical members.
Yeah. Okay. Any other questions? If you have questions, please send them into the Q&A. It looks like we are good to go. And if you have other questions and we move on, please type them in, and at the end we'll get Hank to answer additional questions. Okay, Hank, thank you so much for your presentation. Really kind of a sensitive thing to be excavating that deep right next to that tall tower, for example.